Okay. I'll hide the presenter view. Okay, I think now I hope you are able to see the screen. So I welcome you to the fourth week of the live sessions for the course Basics of Finite Element Analysis Part 2. So the course instructor, as you might know, is Professor Dr. Nachiketa Tiwari from IIT Kanpur. So introducing myself, I am Vikram Balaji, a research scholar from the Department of Mechanical Engineering at IIT Madras. So this is the week 4. So totally you might know that there are 8 sessions. So this is the 4th session. So let us go into the session. So these are the brief contents of the week 4 lectures. So what we would have started in the week 3, so Gaussian quadrature. So it was introduced in the week 3 lectures itself, and some more details about the Gaussian quadrature are continued in this week 4. So apart from that, there another quadrature method or an integration scheme called Newton-Cotes quadrature has been introduced in the week 4 session, and after this small introduction to two-dimensional FE problems. So till now we have been majorly dealing with one-dimensional finite element problems. So either our coordinate was x, so either x or y or z. So it was a single variable problem. So from in this week we would have introduced a two-dimensional problem. So we have x and y coordinates.
Hello sir.
Yes. Hello.
Sir, where I can find the syllabus of Finite Series basic Finite Series?
The syllabus you can find in the course module. So are you registered for the course?
Yes sir, but I get a lot of reminder for I am not understanding what are you going with me.
So you means you are able to log in and in the NPTEL Swayam site, right?
But sir, I got a message on my Gmail.
Okay.
The message I am reading now.
Yeah.
Give 1 minute.
Okay. Okay.
We have a last date of reminder 11. Last date to register for March 2022 this exam. Don't miss to register today.
Yes. That is for exam. So are you planning to give the exam for this course?
Yes sir, but where and how can I register sir?
You can go to the website. So I'll try to show this. Suppose this is your website. So you can click here, right? So are you able to see this? Register for the certificate exam. So are you so here you have to log in. So using your credentials. So let me log in using mine. So once you are login, so you can see here there are the exam form is there. So you can select, you can first fill your personal info. Yes. And so all your details will be there, your address, phone number, all those things. Then you have to go to the courses which you have registered. So you can add. So here you can add this thing. So for me it is showing something. So new course and exam day. So if I select this, so I will get 30th April or something. So if you are registered in this course, you will get this thing, basics of finite element analysis part 2. Here you will get it. Then you can select the exam day. So for this it is coming 30th April or something. And then once you select the courses, you can go to the city. So for first you have to select the course, and then you can select the where you want to give the exam. So this is one thing. Yeah. So you can add other courses also. So for me only one course is there, but for you, if you see, you will have this basics of FE also. So that's so once you select the city, you can just review and finish. Maybe you have to pay some amount. So you have to passport size photo, then your signature also you need to upload here. So the mobile number, all these details you can see here. So once you fill everything, you can register for the exam. So is it okay?
Okay, sir.
Yeah. Okay. So now we will go back to the this thing course. So we'll go to the presentation now. Okay. So as I was telling, uh, so once so one request. So once your doubt is clear, you can try to mute your mic. So because some sound may come. So when you are having any doubt, you can open the mic and then you can ask your doubt. So this is my small request. So thanks. So as I was telling, some Gaussian quadrature, though it was introduced in the previous week, in this week we are continuing some concepts of Gaussian quadrature, and then we introduce another form of new integrations, numerically integration scheme called Newton-Cotes quadrature, and third one is two-dimensional FE problems. A small introduction. So as I told, till now we are mainly dealing with one-dimensional FE problems with x coordinate, you can say, but real life problem we may have a 2D or 3D problems. So 2D problems you can say it's x and y coordinates, and in x and y coordinates how to there are some FEA problems. So small introduction based on that was given in the week 4. So we will now proceed to solve some sample assignment questions. It will be both in the subjective and the objective pattern. So we will these questions are mainly related to the contents which we learnt in the week 4. So we will see them one by one. So we will go to the first question. So this is the first question. The minimum number of quadrature points recommended for numerically integrating a polynomial of order 6 using Gauss quadrature scheme accurately. So we know that Gauss quadrature uses a number of quadrature points. So here he is saying that a polynomial of order 6 is being the function. So number of quadrature points, that will be minimum number of quadrature points that will be needed to numerically integrate the polynomial of order 6. So can anybody take a guess what could be the minimum number of quadrature points required? So order is 6. Okay. So one choice is D is equal to 4. So any other guesses? So okay, so we will now go to see the answer. Yes, you are right, answer is D is equal to 4. So basically you have this for like convention. So whenever if your polynomial is of order say this thing order 6, here you are mentioned. So you can say for even number, if your R is equal to 6 order, so you can say that it is, sorry, it's not R. So usually we designate in the course as P. So R is the number of quadrature points actually. So your P is 6. So I will choose the pen. P is 6. So R is equal to P by 2 plus 1 if P is even, or if P is odd, you can say it is P plus 1 by 2. So here P is even, so you can say it is 6 by 2 plus 1. So which is 3 plus 1 4. So answer is 4. Otherwise, if you are familiar with the second formula, you can still substitute 6 plus 1 by 2, you will get 7 by 2, which is 3.5. So you have to choose the next higher order, which is an integer. So we cannot have a number of quadrature points which is 3.5. So we go for the next high. So that is, you can say it is 4. So either way you can say this is the convention which we are using. So if your polynomial is of order 6, the function which you are going to integrate. So, the minimum number of quadrature points required is this for convention, which is either p by 2 plus 1 if p is even, or p plus 1 by 2. So, this is a whole divided if p is odd. So, answer is D. So, yes, it's a correct answer. So, we will go to the next question. So, if there is any doubt, you can please ask, you can interrupt and ask immediately. So, okay. So, we are now dealing with a subjective question. So, we have a function evaluate I is equal to integral 0 to 4 t times of e power 2t dt using 2-point and 3-point Gauss-Legendre quadrature schemes, and compare the error obtained in both the schemes. So, this is our function. So, we will start to solve this question. So, first we will write what is Gauss quadrature. So, as you might already know about Gauss quadrature, so it is defined in the natural coordinates. So, what is natural coordinates? Can anybody tell? So, how it is different from the normal coordinate? So, suppose we have a x coordinate, we have how to what is the natural coordinate? So, I can depict it as some zeta. So, this is my a to b, for example. What will be the coordinates in the natural coordinates? So, can anybody guess? We have already seen this last week, I think. So, once again I am trying to revise it. So, natural coordinates means your coordinates will be -1 and +1. So, this is the extent of your element. So, this is a one-dimensional element. In a one-dimensional element, you can say not a and b, or we can type as xa and xb. So, since we are referring to x coordinate, so from xa to xb, whatever this is the extent of your element. In the natural coordinates, we are converting it to -1 to +1. So, this is the conversion. So, here you can see it is given in the normal coordinate system from 0 to 4. And what is the relationship between x and eta? So, first we have to see that. So, how we are converting this? We are converting through some x is equal to some function of eta. So, let us assume that we are going for a linear transformation. Why we are going for linear transformation is, since it is only one dimension, it is enough if we go for a linear transformation, and it is a straight line. If it was a two-dimensional, means it can be a curved domain or something else. So, for that we can go for higher order transformation. So, linear transformation is, let me say x is equal to some a, let me not put a, okay, we can say a only, a plus b times of eta. So, which means my transformation is a straight line. So, linearly relating a and eta. So, two conditions we need. So, when x is equal to 0, so let me say my xa is 0 here, xb is 4. So, when x is equal to 0, my eta is -1, and when x is equal to 4, okay, sorry, my eta is equal to +1. So, I just substitute these two relations and I can get what is the value of a and b. It is very simple. So, I just substitute 0 is equal to, okay, I think I will use this one, or probably I will use the note. This is more comfortable to write. So, I have to, my thing is, I have to integrate. So, this is week 4. So, please whenever you are not able to follow anything, you can just interrupt and ask a doubt. So, what we are supposed to do? We are supposed to integrate this t e power 2t dt using Gauss-Legendre quadrature. You can simply call it Gauss quadrature also. But if you see, look up in the internet, there will be lot of quadrature like Gauss Hermite quadrature will be there. So, Gauss under Gauss quadrature there are many examples. but specifically we are using Gauss Legendre quadrature. This you can also call it as Gauss quadrature in general. So 0 to 4 t to e power of 2t dt. So actually we are supposed to for Gauss quadrature we have to do the integration in the natural coordinates. So my t is here ranging from 0 to 4. So this I am going to convert to eta. I can call it zeta from -1 to 1. So as I told earlier I was doing with respect to x. Here I'll just change it to t because we are a question is in terms of t. So t is equal to a plus b times of eta. When t is equal to 0, eta is equal to -1. When t is equal to 4, eta is equal to 1 plus 1. So I substitute this. 0 is equal to a plus b times of -1. So 0 is equal to a minus b. So the next relation is 4 is equal to a plus b times of plus 1. So 4 is equal to a plus b. So these are the two equations. If you add them together, you can get 4 is equal to 2 times of a. So a and a are adding, b and b are getting cancelled. So a is equal to 2. This is my one relation. Again you can get b is also equal to 2. You can substitute a is equal to 2. 2 plus 2 is 4. So b is also equal to 2. So finally we have the relation t is equal to 2 plus 2 times of zeta. So this we are now going to substitute in this integrate. So again I write it 0 to 4 t into e power 2t dt is equal to -1 to +1. T I substitute 2 plus 2 times of zeta, e power again 2 into 2 plus 2 times eta, which is you can get 4 plus 4 times eta, and dt. So what is dt? From here you can get dt is equal to 2 times of d eta. So 2 d eta. So I multiply this 2 and I simplify it further, -1 to +1. So 2, so you get 4 plus 4 times of eta into e power of 4 plus 4 times eta d eta or zeta. So this is my function capital F of eta d eta. So finally I have got this in some format, which is -1 to 1 f of eta d eta. So this f is different from small f. Small f we used for this one. So this is capital F. Okay, so I have to solve using two methods: 2-point Gauss and 3-point Gauss. So first let me use 2-point Gauss. So you can say the general equation for Gauss quadrature is, so any integral from -1 to 1 f of eta d eta is equal to, you can say it's a summation from I is equal to 1 to r. You can say f of eta I into wi. So what is this? This is the quadrature point. Eta I is the quadrature point, wi is the weight associated. For 2 points we have r is equal to 2, which means I can be 1 and 2. So we have eta 1, eta 2, w1, w2, and our element is from -1 to 1, and so our eta 1 and eta 2 will be somewhere inside. So can anybody guess what is eta 1 and eta 2 for a 2-point quadrature? So we saw this last class also, and it is explained in the lecture also. So eta 1 and eta 2, can anybody explain what is the values? So you can so if you want to answer, you can open your mic and you can guess the answer. Eta 1, eta 2, any guesses? What are the points?
This will be ±0.577.
Yes, ±0.5773. So how it is occurs means it actually it is a minus of 1 by root 3, you can say, and this is plus 1 by root 3. So if you calculate 1 by root 3, let us see what you are getting. 1 by root 3 is nothing but 0.577350. So this is our actual thing, but in reality it is minus 1 by root 3 and plus 1 by root 3. So that's how it comes. So there is a derivation also, we might have seen last lecture. I might have derived how this value comes. Maybe if you are interested in how this value came, we can look maybe in the later part of the session. We can look how this value has come. And W1, W2, what is be the values? So E1, epsilon, eta 1, eta 2 we saw. What is W1, W2?
1, sir.
Yes, 1. So which means my formula is going to now become that, let us say my integral is I. So it is going to be f of eta 1 into W1 plus f of eta 2 into W2. So f of eta 1 is, what is my f? So it is e power 4 plus 4 eta 1. I think we have, it is, yes, 4 plus 4 eta 1 into e power 4 plus 4 eta 1. So before this I have to write that one, eta 1 into e power 4 plus 4 eta 1 W1 plus 4 plus 4 eta 2 e power 4 plus 4 eta 2 W2. So let me call this as I1, let me call this as I2. So I am going to separately solve it. So I1 is, you can substitute eta is equal to that minus 0.577. So I will just substitute minus 1 by root 3. So 4 minus 4 by root 3 into e power 4 minus 4 by root 3. W1 is 1. So you can also calculate in the calculator simultaneously. So I'll do this now. So this value is coming to be 1.690598,923. So what is this e power? So this is some 5.42272753. So if I multiply both, what I am going to get? I am doing the multiplication. I am getting something like 9.1676573224. So please check whether this is correct or not. So I have got this value. So I can now go towards I2. So I2 will be, instead of minus, you will simply have plus. So 4 plus 4 by root 3 into e power 4 plus 4 by root 3. Again your weight is again going to be 1. So let me calculate this. So 4 plus 4 divided by root 3, my answer will be, for this is 6.309401077 into, so this is coming 549.7156127. So if I multiply both, so 4 plus 4 by root 3 I am going to multiply. So I am getting something 3468.376279. So are you also, I hope you are also getting the same answer. So I just now add both. I is equal to I1 plus I2. So which is 3468.376279 plus 9.167657324. So this is coming out to be 3477.543936. This is my 2-point answer. So what we will do next, we are going to do calculate using 3-point. So after we calculate the 3-point, we will evaluate the integral in the exact manner and try to compare the error in both. So I hope you are following. So is there any doubt till this? So we just computed the 2-point quadrature. So let me now go for 3-point quadrature. So 3-point quadrature, your I will be equal to summation equal to 1 to, you will have 3 points, f of eta 1 eta I wi, which is f of eta 1 w1 plus f of eta 2 w2 plus f of eta 3 w3. So in a 3-point quadrature, I have 3 points. Okay, I think somebody is trying to enter. Okay, so -1 to 1, this is my natural coordinates, and we have 3 points, epsilon 1, epsilon 2, epsilon 3. So what are these epsilon 1, epsilon 2, epsilon 3, and what are w1, w2, w3? So can anybody tell what are the answers? So I mean for this epsilon, eta and w. So this is eta. So sometimes by mistake I am calling it epsilon. So it's actually eta which I am writing.
Plus or minus 0.7745 and
Yes.
another one is 0.
0. Okay. So this value, if you see, it is actually nothing but square root of 3 by 5 plus or minus. So if you just do 3 by 5, it's nothing but 0.6, no? So if you take square root of 0.6, you will get this exact thing. So you will get plus or minus 0.7745966692. So this is the bigger thing. So you can round it off, you can say up to 5 decimals, or you can say up to 6 decimals or something. You can keep that value. Maybe you can round it off to 7. This 6 will become 7, I think, something like this. So actually this will be root minus 3 by 5, this will be root 3 by 5. So this will be 0. So what is w1, w2, w3? That will also be some, yes,
0.88.
yes, 0.8888. Yeah, and that is w1 and w3. w2?
0.555.
Okay. Oh, I think I have made a mistake. This will be w1 and w3 if I am not mistaken, and this will be w2. Correct? Middle one will be bigger. Is it, or yes, for 0 it will be
0.88.
okay, which means it is w2. So e2 is epsilon 2 is 0, and w2 will be this. You can say it is 8 by 9. So 8 by 9, if you calculate, you will get that 0.8888, that value. So this will be 5 by 9 actually. So both will be 5 by 9. So I don't think I hope there is no doubt in this quadrature points for the 3-point quadrature. I'll just erase these things. So now what is f of epsilon 1 w1? So again I am splitting into 3 parts. This will be my I1, this will be my I2, this will be my I3. So I1 is f of epsilon 1, eta 1. So what is that? You have so 4 minus 4 square root of 3 by 5 into e power 4 minus 4 square root 3 by 5. So it's actually, you can see if you go before. So that is why f of this thing. So this was the f, right? 4 plus 4 times of eta into e power the 4 plus 4 eta. So in place of eta I am substituting eta 1. This eta 1 is minus of square root of 3 by 5. 3 by 5. So if I calculate this, what is the answer? 4 minus 4 root 3 by 5. I am getting this to be around this portion is 0.9016133323. And what about this E? Let us check. So I am getting some into 2.463574448. So if I add both, if I multiply both into square root of 3 by 5, so something 2.2211914545. This is my I1. Let me go below. Let's now calculate I2. F of eta 2 into W2. Okay, this is, I forgot to multiply by 5 by 9. So this will be 1.233995,303. Where is this? I'll write it little below. I2 for eta 2 W2. Eta 2 is 0, so which means this 4 minus 4 into 0, it will become 4. Same for here, 4 into e power 4 into 8 by 9. So what is 4 e power 4? 4 into, so this is coming out to be 218.3926001 into 8 by 9 into 8 divided by 9. So this is around 194.126757. Okay. So now I3, f of eta 3 W3, so which is 4 plus 4 square root of 3 by 5 into e power, same thing, 4 plus 4 square root of 3 by 5 into weight is 5 by 9. So I will calculate this again. Into this is 7.098386677 into e power, the same thing. This is 1210.013357 into 5 by 9. If I multiply everything, I am getting something around 4771.745938. Okay, so if I add everything, I is equal to I1 plus I2 plus I3. What was my I1? So this one is 1.2. Okay, I'll add from backwards. Let me add, I have this. Now I'm going to add I2, 1.194.1267557 and plus 1.2 233995303. So something I'm getting 4967.106689. So are you also getting the same value? This is for my three point quadrature. Think sorry. Okay. Yes. So this is 3-point quadrature. So we'll compare the what we got for 2-point. For 2-point it was 3477.54. Here we are getting 4967. So we are value has been increased. Let us see what is the original value. So we can compare the error for both. So originally our function was integral 0 to 4 e power 2t t e power 2t dt, right? I'll go to the top. Yes, 0 to 4 t e power 2t dt. So till now we calculated for both 2-point and 3-point quadrature. So this is, you can say, integrate by parts. So this I am going to, so my u is equal to t, dv is equal to e power 2t dt. So v I am going to integrate it, it will be e power 2t by 2. So du is dt. So integral of u dv is equal to uv minus integral v du. So I am going to use the integration by parts. So which means uv t into e power 2t by 2. This will go from 0 to 4 minus integral 0 to 4 v e power 2t by 2 dt. Okay. So if I calculate this, 4 into e power 8 by 2 minus 0, think the entire thing goes to 0. So because it is 0 into, so this is the thing, minus integral. So again this will become, if I multiply and divide by 2, so if I take this 1 by 4 outside, it will become integral of 0 to 4 e power 2t into 2 dt. So which is going to be simply e power 2t from 0 to 4. So 2 e power 8 minus 1 by 4 into e power 8 minus e power 0, which is 1, which is 2 e power 8 minus e power 8 by 4 plus 1 by 4. What is the real answer? E power 8 into 2 minus 1 by 4, which is 1.75 plus, so I get a value as 5216.926477. Okay, so we can see this is 5216. In 3-point quadrature we got 4967, and in 2-point quadrature we got 3477, which means our 3-point quadrature is more accurate, but still it is not accurate enough. So there was some, let us see what is the error percentage. We can say equal to calculated minus actual by actual into 100. So what is the calculated for point? You can say this is 3-point quadrature. For 3-point quadrature 4967. So let me put absolute value, because it could be negative, so I am taking absolute value. So my calculated minus actual, the it is coming around 249.81978883. My actual is this value 5216.926477 into 100. around 4.788% error. If I do the same for 2 point, so what will be my calculated minus actual? My actual is 5216, but my calculator is much lower, something in 3000, yes, 3477, 543936 minus 5216.926477. It's coming around 1739.382541 divided by 5216.926477 into 100. So I think this will be in double digit error, I think, percentage wise. Approximately 33% error. So you can see the comparison. For 3 point is 4% of error, but it is 33% in the 2 point. Maybe in 4 point this error will be much lower, it will come to maybe below 1% also, but we have to calculate and see. Maybe you can calculate this, but our question demands only 2 point and 3 point. So we have calculated that. So any doubt in this question 2? So this was a subjective question. So if there is no doubt, I will proceed to the next. So we just have to first convert the domain from the natural to the from normal to the natural coordinate system, find out the transformation, and appropriately we have to choose the quadrature points and the weights associated. If it is 2 point, then it will be two quadrature points and 2 weights associated, and if it is a 3 point, then we have 3. So based on that, we calculated the integration and we compared with the actual value of integration. So we see that as we increase the number of points for the quadrature, the error is minimized, is becoming more minimum. So let us go to the question 3. So we have to evaluate the following integrals using the Gauss-Legendre quadratures. So earlier we just saw some function like simple function of t. Now we are trying to solve some element stiffness matrix component. So we have some stiffness matrix. This you can say it's either this is also some other matrix component. So we have this psi 1 psi 2 which is defined, and psi 1 and psi 2 are the Lagrange linear interpolation functions. Okay. So can anybody say what are psi 1 and psi 2 values? So you first in terms of x, then in terms of eta. So if you know either one, you can simply say either in terms of eta or in terms of x. So what would be psi 1 value, what will be psi 2 value? So your element is from xa to xb, this is your x. So you have some value of psi 1 which is going from 1 to 0, and psi 2 simultaneously goes from 0 to 1. So we would have seen in the earlier classes or in the lecture. So those who have followed the lecture, they might know what is psi 1 and psi 2. If you don't know, then I will write down the value of psi 1 and psi 2. So does anybody know what is psi 1 and psi 2, or in terms of eta at least? So in eta this will be minus, yes. So it will be minus is this or it like this, are you telling?
Yes, sir.
Minus eta by 2 into 1 minus eta. Okay. So what about psi 2? So it will be okay. I think this is a okay. I think this is quadratic, right? What you are telling. So this is linear actually. So linear, quadratic you will have psi 3 also, but here in linear we are going to deal only with psi 1 and psi 2. So I think this will be, this is the thing you are trying to say, but we are dealing for the linear. So for linear, psi will be different. I hope there is no confusion. Okay. So this is for quadratic actually. So I will write in terms of linear ones. First I will write x and then I will write the eta. So this will be xp minus x by xb minus xa. So this will be x minus xa by xb minus xa. So does anybody remember this? This is a simple linear one. So how we are getting this? Maybe we can, it's easy to derive actually. Sorry. So I think we'll see the derivation probably later if you have some time. So if you substitute x is equal to, yes, any doubt? Okay, so in terms of psi, in terms of eta, you will have minus half of or rather sorry this. So this will be psi 1, psi 2 will be is it okay? It's a linear thing because it's dependent on power is 1. So in the previous one what you answered, the power is 2, it is a quadratic. So this here I have mentioned it's a linear interpolation function. Yeah, okay. So I hope this is okay. So this is the two, psi 1 and psi 2. So I am going to go for the notes. So I am going to write this k1 and k2. So probably I will open a new page, I'll add a new page. So this is for the next question. So k12 was integral of xa to xb x naught plus x into d psi 1 by dx into d psi 2 by dx into dx. Is that the case? Yes. So xa xb, this is in x coordinate, in zeta minus 1 plus 1. So let's assume the transformation like this, at x is equal to xa minus 1 which means add both xa plus xb by 2. So if you substitute b, if you substitute this in either of these two equations, so what will I get? B is equal to I'll get something like this, I think. Let me check. So xb is equal to xa plus xp by 2 plus again xb minus xb. Okay, I think this is the one. So my x is equal to a xa plus xb by 2 plus xb minus xa by 2 into zeta. So this is the transformation. So I have been told to use Gauss legender. Okay, so we'll see how much points we require later. So what is dx? It will be, this will vanish, xb minus xa by 2 into this thing. So this you call, so what is this term called? So dx I am relating to d eta. So this we would have introduced in the last week. This this is a particular term which has a name to it. What is that name? If anybody remembers? Yes.
Jacobian.
Yes, Jacobian. Correct. Jacobian. So I can write it as dx is equal to j times of d eta. Okay. So I just have to substitute this x value as this one, and I have to compute d1 d psi 1 by dx, right? Okay, what is psi 1? In terms of x it was xb minus x by xb minus xa. So in terms of eta it is half of 1 minus eta. So how did this come? Transformation. So again you have d psi 1 by dx is equal to d psi 1 by d eta into d eta by dx. Is this okay? So what is d psi 1 by d eta? You can simply differentiate this. I think it will be minus half, no? This, what is d eta by dx? So dx is equal to j d eta by dx, which means it will be 1 by j minus 1 by 2j d psi 1 by dx. Okay, what is d psi 2 by dx? Psi 2 I will write it. D psi 2 by d eta into d eta by dx. It will be half into 1 by j, which is 1 by 2j. Okay. Now finally I have to substitute everything. X naught plus x into d psi 1 by dx into d psi 2 by dx into dx. This is from xa to xb. So I am going to write everything in terms of eta, minus 1 to 1. X naught is a constant, so we can be as it is. X I am going to write it in this term. This whole thing I am going to insert inside. So this is the thing. Sorry, d should not write. It's only eta. D psi 1 by dx, it is 1 by 2j, sorry, minus 1 by 2j it was here. This is 1 by 2j, and dx, what is dx? Dx is j times of d epsilon d eta. So if I minus this, so I will get minus 1 by 4 I can take outside, right? And j also I can take outside because j is a constant. What is j? xb minus xa by 2. So what is remaining in the integral? This one, so only this whole thing I have taken outside now. So what is remaining is this part, x naught plus xb by 2 plus xb minus xa by 2 epsilon, the whole thing multiplied by d eta. Okay, so minus 1 by 4j. So j I am going to substitute now. It was xb minus xa by 2. X naught plus xa plus xb by 2 plus xb minus xa by 2 eta. So this is my f of eta. Two times of xb minus xa, integral minus to 1 f of. So what is the order? Can anybody say what is the order of f of eta? So eta, is it first order or second order, linear or quadratic, or what it is, function?
Linear, sir.
Linear. So which means order is 1. So if my order is 1, so let us say it is a linear polynomial. So what is my number of quadrature points required?
2.
Okay, 2. So what's the formula? So you have, this is p. So how we find out r? We just saw in the first question, no? So for odd we have one formula, for even we have one formula. Here 1 is odd, so it will be p plus 1 by 2. Is it okay? So we saw, do you remember in the first question we saw this, right? So if I put 1 plus 1 by 2, it's nothing but 1. So we can do with one point quadrature also. We can do 2 point also, that's not an issue. But for simplicity, we can go for 1 point itself. So what is 1 point? 1 point quadrature, does anybody remember? So this is your minus 1 to 1. What is your E1 W1? 1 point quadrature. It's not 2 point, 1 point. What is eta 1? What is W1? Does anybody remember? Any guess?
0, sir.
Yes. W is
2.
Yeah, okay, so correct. So we are going to follow the same thing here. So what is my f of 0? This is my function which I have written in the top. So x naught xa plus xb by 2 is going to come the same, plus xb minus xa by 2 also, they are constants, and eta is 0. Okay, so this is my f of 0. Correct? I have just substitute e is equal to 0, which means this thing will vanish. It is going to be x naught plus xa plus xb by 2, and w is going to be 2. So which means what I am going to do, I am going to this term I will rewrite minus 1 by 2 times of xb minus xa into f of 0. What is this? X naught plus xa plus xb by 2 into 2. So this is my f of 0, f of eta, and this is the weight function. So 2 you can see. So minus 1 by xb minus xa. So this is going to be my k12 finally. X naught plus xa plus xb by 2. So you can verify this actually. How you can verify? You can simply integrate with respect to eta and find out. So we will do that. This is for exact integration. I did a quadrature based integration. So let us see whether we are getting the same answer. I hope we will get the same answer. I think minus 1 by 2 times of xb minus xa integral of minus 1 to 1 x naught plus xa plus xb by 2 into plus xb minus xa by 2 into eta. This whole I am going to integrate. We just simply did a 1-point quadrature. Now I am going to totally integrate everything. So minus 1 by 2 times of xb minus xa. So I am going a big bracket minus 1 to 1 x naught d eta plus xa plus xb by 2. I am splitting the integral. So this will be minus 1 by 2 times of xb minus xa. This is x naught into d eta is going to be simply eta minus 1 to 1 plus again xa plus xb by 2. This is again going to be d eta, integration is going to be eta again. This is also minus 1 to 1 plus xb minus xa by 2. So eta d eta, what is the integration? Eta square by 2, right? This is going to be minus 1 to 1. So we will see individually. So this was minus 1, right? Minus 1 by 2 times of xb minus xa. This is eta from minus, it is going to be 2x naught plus 2 times of, correct? This will be 1, this will be 1 by 2, again it will be minus 1 the whole square 1 by 2. So 1 by 2 minus 1 by 2 0, so the whole thing vanishes. So it is going to be 0. So this 2 I am going to take it inside, minus 1 by xb minus xa x naught plus xa plus xb by 2. Did we get the same answer? Yes. I will highlight this. So using a single point Gauss itself, we have got the correct answer. So we have verified using both the cases. Any doubt till now? We have solved for the k. So our so we have to solve for g also. So we will solve for g now. So all these are numerical problems. So just so g12 integral xa to xb x naught plus x into psi 1 psi 2 dx. Was it that thing? Let me ensure. Okay. correct. So again psi 1 was dx is j times x is equal to okay, so it's going to be minus 1 to 1 x naught plus xa plus xb by 2 plus xb minus xa by 2 eta into psi 1 psi 2 half into 1 minus eta half into 1 plus eta dx j times g. So j I am taking outside, j times integral of minus 1 to 1 this whole thing. So this eta applies only for this xb minus xa by 2. So half into half. So this 1 by 4 also I am taking outside. J also I took sorry j by 4. Into 1 minus eta into 1 plus eta is 1 minus eta square. So this whole thing is going to be by f of eta. So what is the degree of this equation? So you have e square eta square term here and you have eta term here. So if you multiply, what will be the degree overall? Any guess? What order polynomial is this? So it's nothing but a cubic, right? Third order. Any doubt? Because I have eta square term here, I have eta term here. If I multiply both the functions, I am going to get some eta cube terms. Some term I will get. So the entire degree of the polynomial will be 3, which means highest power. Not every term. The highest power will be a third order. So it will be something of the form ax cube, a eta cube plus p eta something square plus c eta plus d. It will be of this form. If you expand and see, I am not expanding because I am just going to use the quadrature and I am going to directly substitute the value of the quadrature. So third order. So what is the r value? P is 3. What is r value? R will going to be 3 plus 1 by 2. P plus 1 by 2, 2. So I am going to 2-point quadrature. So why 2-point quadrature? Because for have a cubic polynomial and I have which is of order 3, which means r is equal to p plus 1 by 2, which is 3 plus 1 by 2, which is 2. So I am going to use a simply 2-point. So we have already seen in 2-point, so one will be plus 1 by root 3. Both w1 and w2 are going to be 1. So simply, so this j by 4 I take outside. I am just simply going to this thing evaluate this. So this integral will be f of w1 w2. So which means f of eta 1 x naught plus xa plus xb by 2 plus xb minus xa by 2 into minus 1 by root 3. This whole thing multiplied by 1 minus eta square. What is 1 minus? That is 1 minus 1 by 3 you will get. It will be 2 by 3. into W is going to be 1. This is my I1. I2 will be same thing, x0 plus xa plus xb by 2 plus xb minus xa by 2 into, this will be plus 1 by root 3, the whole thing again multiplied by 2 by 3, since because you get the point, right? 1 minus eta square, eta is going to be minus 1 by root 3, 1 by root 3, minus 1 by root 3 substitute will be 1 by 3, plus 1 by root 3 if I put also it will be 1 by 3, 1 minus 1 by 3 will be 2 by 3 into weight is going to be 1. So if I add I1 plus I2, you can see what all the terms you can able to add. So 2 by 3 will be common, so into 1 I can take it out because it doesn't add any value. So 2 by 3 I can take common, so x0 is going to add 2x0, this thing is also going to be 2 times of xa plus xb by 2. And what about this? Minus 1 by root 3 and 1 by root 3 both are going to cancel each other, so I will get a 0 for this term, which means if I take this 2 outside, it is going to be 4 by 3 x0 plus xa plus xb by 2. So this I1 plus I2 I am going to multiply, this was my I, which means for function integration, this I did split into I1 plus I2, and for I1 I use eta 1 and I2 I use eta 2. This integration is now complete. I am just simply going to multiply by j by 4. So what is j? You have to go back to the very beginning. J will be xb minus xa by 2. Already we have a 3 here, into x0 plus xa plus xb by 2. So which means it is G12 is going to be xb minus xa by 6 into x0 plus xa plus xb by 2. So this is the thing we calculated, G12. So any doubt in this? So if you just integrate it directly using this formula, I think you will be able to directly integrate, and you can see that you will again get this value only, because 2 point, if we had have used the 1 point integration, 1 point quadrature, then we would not get an exact value. But since you are using a 2 point integration, and we saw that the 2 point is going to satisfy my exact according to this convention, so I will get the same answer if I integrate it. So you can maybe probably try to integrate it. I will not do. So you can try to integrate it. You can note this down probably and try to integrate and see whether you are getting the same answer as this. You will get, since we already verified for K12, I will now we will look at further questions, because I think we are spending too much time in this. We have spent too much time here. So at least now if you know the Gauss-Legendre quadrature, you can be able to calculate some integration. So that is the objective of this. So I hope there is no doubt till what we discussed. So shall we go to next question? Any doubts in what we discussed? So I hope you are following. Okay, we are following the notes only. So okay, so this back to objective type. So Simpson's rule of numerical integration. So I hope you remember what is Simpson's rule. Simpson's rule is a special case of which one? So one is Gauss-Legendre, Newton Cotes, Gauss-Hermite. This is none of the above. So any guess what is the answer?
B, sir, B.
Yes, B, right? So yes, answer is B. I think somebody, is there any message? Okay, yeah, answer is B. So Newton Cotes, we will just see the formula. So Newton Cotes, what is sorry, a xa to xb. Some f of x dx. This is going to be into summation I is equal to 1 to r f of xi wi. Okay. So this formula is there's no doubt in this formula, no? So this is a general Newton Cotes formula. So Simpson's rule we'll recall. So you have 2 points xa xb and a middle point also, xa plus xb by 2. So what is f? Is equal to is going to be 1 h by 6, no? H by 6, h is the total, h by 6 into f of xa, right here only, plus 4 times of so this is the Simpson's rule, h by 6, h is nothing but xb minus xa, the length of the element, to total length of this element. Here we are having 3 nodes, we are having 2 nodes, additionally we have a middle point. So this was the formula. So we can say this is also our h. So let us try to do for this thing. So if it is a 2 point means h into f of sorry, you say this is going to be 3 point actually, f of xa w1 plus f of xb xa plus xb by 2 w2 f of so if you see for 3 point Newton Cotes, what was the weights? Does anybody remember? Okay, we'll start from 1 point. What is w1 and what is x? Anybody remembers what is for 1 point, what is the weight? Let me erase x. So basically you are dividing into into, if our number of quadrature points is r, so each will be xb minus xa by r minus 1. So 1 point, if you see, means, so r is equal to 2. So xb minus xa by 1. So there are two quadrature points. Sorry. So w1 will be just 1 for 3 point. So your weight will be half. Oh. So here it will be 1 by 6, 4 by 6, 1 by 6. So if I substitute this 1 by 6, 4 by 6, 1 by 6, I will directly get the Simpson's rule. So Simpson's rule is nothing but is a special case of Newton-Cotes quadrature where there are two, three. There are 3 points, no? 1, 2, 3. So this is 2 point. This is 1 point. So this was 1 point. This was 2 point. This was 3. So any doubt? So it's a 3-point Newton-Cotes actually. So 1 point means you will have simply some any point. It can be anything, and your weight will be 1. So 2 point is how W1 and W2 are half. So which means you have 2 end points, which are these 2. The 3 point means you will have already the 2 nodes, and then you will have 1 node in between. That is a 3-point Newton-Cotes quadrature, and these are the weights. So any doubt? Shall we go to the next question? So its answer is B. I was just explaining what is the Newton-Cotes quadrature.
Yes sir. Yes sir.
Okay. So I think we already saw in the last question the quadrature points ranging from xa to xb in a Newton-Cotes integration scheme are dash, and the end quadrature points are dash compared to the end nodes. So I have a thing like this element. This is going to be xa, this is going to be xb. So I have many quadrature points. I can have many quadrature points in between. So quadrature means I am including the end nodes also. So all these points are they either equally spaced or unequally spaced? So how will they be? The spacing will be same, equally spaced or unequally spaced in a Newton-Cotes. I am asking Newton-Cotes quadrature. Yes, equally spaced. Okay, so which means either A or B. So equally spaced is there in both. And end quadrature points, are they same as the end nodes? Are they different than the end nodes? End quadrature points. So all are quadrature points, you can say. So xa, xb, are they end nodes? So are they the end quadrature points as well? I am asking. Are they same compared to the end nodes, or are they different?
Same.
Yes, same. So A is the answer. Only thing is, if you note if you have gone for the Gauss quadrature, you will have quadrature point somewhere here. These are only the quadrature points. So the end quadrature points, they are not the same as the end nodes for Gauss. But for Newton-Cotes, what we are doing is between xa to xb, we are splitting the domain into equally spaced elements, and so the number of quadrature points are r means, so you will have r minus 1 divisions, and x a and x b are part of this quadrature points. So it are both equally spaced and it is same compared to the end node. So answer is A. So let us go to next question. So the spacing between the quadrature points in a Newton-Cotes integration scheme with r quadrature points. So r quadrature points means, so x a, x b, already 2 are there. So totally let us say some r quadrature points are there. So how many divisions will be there, and what is the spacing? And what are the sum of the weights?
So D is given as x raised by r plus 1.
Okay. So let us see answer. Yes, you are right. So since I have r quadrature points, there will be r minus 1 divisions. And since there are r minus 1 divisions and they are all are equally spaced, what it will be spacing is the total length xp minus xa divided by the number of divisions. So this will be my spacing. And if you see the sum of the weights for, let us say, trapezoidal rule. Trapezoidal rule is basically you have xa and xb and simply these 2 points, and your formula is, let us say this length is h by 2 into f of xa plus f of xb. If you remove this h, I am writing h separately, so I will get half. So these are my weights. So half plus half 1. Typically, and the same if you go for the Simpson, it will be 1 by 6 plus 4 by 6 plus 1 by 6. This is again 1. So what will be for this is was a 3 point Newton-Cotes. So for 4 point, what will be the weights? Can anybody tell? Here 1 by 6, 4 by 6, 1 by 6. What will be for 4 points? Can anybody remember and tell me?
Sir, 1 by 8, 3 by 8, 3 by 8, 3 by 8.
1 by 8, 3 by 8, 3 by 8, 1 by 8. So if you sum up these also, what you are going to get? 3 plus 3 6, 6 plus 1 7, 7 plus 1 8, 8 by 8. This is also 1. So any Newton-Cotes scheme, if you sum up the weights, you will get as 1. You can try it for r equal to 5, r equal to 6 also. Okay, let me try for can r equal to 5, can anybody mention? What are the quadrature points?
So 7.90.
Yeah, 32. Then okay. So basically these are going to again repeat itself, no? Yeah. So this you see here also 32 plus 12 44, 44 plus 32 is 76. 76 plus 7 is 83, 83 plus 7 is 90. So again it's 90 by 90 1. So always the sum is equal to 1, and this is going to be xb minus xa by r minus 1. So why r minus 1 is, since I already have r number of points, the divisions will be r minus 1. So the sum of each will be this much. So that was the thing. Let us go to next question now. In a 4 point Newton-Cotes quadrature, what are the quadrature weights associated with the function value at the end nodes? So 4 point means xa xb. 4 points means I am going to add 2 more points. So totally I have 3 divisions. And what are the weights associated with endpoints? W1, W2, W3, W4. What are W1 and W4? 4 point. Just we saw, right? for 4-point quadrature. What was the value?
1/8.
Yes. And these will be 3/8, 3/8 respectively. So already remember the formula is integral of xa to xb f of x dx xb minus xa into summation I is equal to 1 to r f of xi wi. So answer is D. So this is the Newton Cotes summation. This you already have xb minus xa endpoints, and if you multiply both, that will be the value. So 1/8. So if it was, you can say f of x1 w1, f of x2 w2, f of x3 w3, this one. So next I am going. So the maximum order of the polynomial that can be numerically integrated accurately using 5-point Newton Cotes quadrature. So 5-point Newton Cotes quadrature, r is equal to 5. And what is p? What is the maximum order of polynomial I can numerically integrate? So remember, for first of all, this p and r relation, will it be the same as Gauss-Legendre or will it be something different? Is it same or different? So are you understanding? Which means, so if the polynomial order is p and I have a relation for r that relates to p, so that relation we saw for Gauss-Legendre, r is equal to p by 2 plus 1 if p is even, p plus 1 by 2 if p is odd. Will that same hold for here or will it be different? Can you guess? Some guess. Will it be same or different? Okay, so if you don't know, I will tell the answer. Answer will be different. So now I told it is different. What is this p? Okay. So if you are not aware, I will once again tell you. For Newton Cotes quadrature, p is equal to r if r is odd, and p is equal to r minus 1 if r is even. So here what is the answer then? I have told the formula also. So what's the answer? So 5-point Newton Cotes, what is the maximum order of polynomial? So I am asking what is p? Yes, 5. So r is odd, no? So it's r. Yeah, answer is C. So remember, this is for Gauss. So you can see that Gauss-Legendre, it will achieve exact integration with a lower number of points. So if here, if p is if r is 5, okay, I will rather put it this way. So we know that 5, I have a 5th order polynomial. So for 5th order polynomial, number of quadrature points I require in Gauss-Legendre is 3. I can do the integration using 3-point quadrature, but for Newton Cotes I require a 5-point quadrature. So this is the difference, which means for the same degree of polynomial to be integrated, I can get a more accurate result in the Gauss-Legendre quadrature for a lesser number of quadrature points. I hope you understand. So now we are going to go to the next question. Okay, we totally have 10 questions, 9, 10, 11. So we'll quickly see this question. So f of x, I have f of x. I am going to use the notes. I'll add a page. F of x 0.2 plus 25x minus 200x square plus 675x cube minus 900x power 4 plus 400x power 5. I have to integrate from 0 to 0.6. What was the quadrature? 4-point Newton quadrature. So 4 point xa is 0, 6.6. 4 point means I am going to add 2 more points. So I have 4 points. So this is my point 1, point 2, point 3, point 4. So what will be 2 and 3? Equally spaced, no? So it will be point 2, point 4, equally spaced. 4 point Newton Cotes. Okay, I have the points. Now tell me the weights. You already see, right? Can anybody tell the weights? What is going to be one W1, W2, W3 for Newton Cotes? You just saw, right? I will write 1 by 8, 3 by
3 by
8.
8, 3 by 8, 1
Yes.
by 8.
Yes. Okay. So what is the formula? 0 to 0.6 f of x dx is equal to 0.6 minus 0, that is xb minus xa into summation. Which means I am going to develop a table I 1, 2, 3, 4. What is x value? 0, 0, 0.4, 0.6. xi I have, then I have I. What is f of xi? And what is, okay, f of xi we will see next. First we will see wi. Wi already mentioned, 1 by 8, 3 by 8, 3 by 8, 1 by 8. F of xi. What is f of 0? Substitute 0 here, 0, 0, 0, 0, 0. It will be 0.2 answer. F of, then f of 0.2. Can anybody quickly multiply 0.2 and tell me what's the answer? Okay, I will also simultaneously do. So 0.2 plus 25 into 0.2 plus, sorry, minus 200 into 0.2 square plus 675 into cube minus 900 into 0.2 power 4 plus 400 into power 5 I am getting something like 1.288. Are you getting something different? I don't hope so. So let me check.
Same answer.
Yes, okay. Thank you for the confirmation. So 0.4 we will do now. 0.2 plus 25 into 0.4 minus 200 into 0.4 square plus 675 into 0.4 cube minus 900 into 0.4 power 4 plus 400 into 0.4 power 5. I am getting something 2.456. Okay, so please verify this also. If you get something different, please inform me. I will recheck my calculation. So now 0.6, 0.2. So this is the answer, 2.456 for 0.4. So once verify this and he tell to me if my calculation is different from what you are getting. I will recheck once again then. So I will go for 0.6 now. 0.2 plus 25 into 0.6 minus 200 into 0.6 square plus 675 into 0.6 the whole cube minus 900 into 0.4 power 4, sorry, 0.6 power 4 plus 400 into 0.6 power 5 minus 19.576 I am getting. I think somewhere I will recheck once again. So this one, did you check? 2.456, did you get it or you got something else?
Yes, sir. 2.4560.
I think
And
I'll
I don't think minus 19.5.
okay, I will check this once again because I think somewhere I have made some mistake. So 2 plus 25 into 0.6
I think 3.4640.
yeah, I'll check it. Square okay. So now I recalculated, it's not minus 19, it is actually 3.464. So I hope this is the answer you are also telling, sir. 3.464.
Yes, sir. Yes, sir.
Okay. So we will now f of xi wi. We will multiply both. So this column and this column I am multiplying. So 0.2 into 1 by 8. 0.025, 0.288 into 3, 0.483, 2.456 into 3, 0.921. Please check these values also simultaneously. 3.464 into 1 by 8, 0.433. So if I sum everything, 1.862 I am getting. So, this summation I have to multiply with 0.6. This is the value of integration which I got using the 4-point quadrature, Newton Cotes. So, I hope you also get the same answer, 1.1172. So, actually we will try to integrate it using the conventional direct, and we will see how far we are from the original answer. As I told here, so since we have a fifth order polynomial in Newton Cotes, we should have at least 5 points. So, if you use 5-point quadrature, you will get the exact answer, but since we are using 4, you will not get the exact answer. We will see what is the exact answer. So, exact answer 0.2 dx 25x dx 200x square dx plus 675x cube (900x power 4) 400x power 5. So, if you evaluate it, 0.2 into 0.6, this will be 0.12, 25x dx, 25 into x square by 2, 25 into minus oh, this was minus 900 plus 400 0.6. Plus 675 power 4 divided by 4 into 675, 21.87 minus 900 power 5 5 13.9968. So, let us add everything. I'm getting 1.2036. So are you also getting the same answer? I'll recheck my calculation once again just for to make sure. Okay, I think my answer is okay. This is for exact. And what was the answer we got for the 4-point quadrature? 1.1172. Okay, I think we have some time. So what I will do, I will use the 5-point quadrature and calculate. Probably we will see this is our last question. I'll just show that using 5-point quadrature we are getting the exact answer. That is what we are planning to do. So if it is a 5-point quadrature, what will be the points? So all will be equally spaced. We will have 4 divisions. Point 0.15, 0.3, 0.45. So for 5 points we will have, which means equally spaced, which means 0.15, 0.3, 0.45 and 0.6. So 0.15 is my division. Okay. So again I am going to form a table I. 1, 2, 3, 4, 5 X. What are the W's? I'll try to recall. I think it will be 7 by 90, 32 by 90, 12 by 90, 32 by 90, 7 by 90. F of xi. Okay, so this will be 0.2, right? And we have already calculated from the table. I think 0.6 is there already. So this will be 3.464. This we can already incorporate inside. So let me calculate for 0.15, 0.3 and 0.45. So please you also calculate, you guys also. So 0.15, 0.3 and 0.45. So I will calculate one by one. 0.2 plus 25 into 0.15 minus 200 into 0.15 the whole square plus 675 into 0.15 the whole cube plus minus 900 into 0.15 the whole power 4 plus 400 into 0.15 the whole power 5. 1.302875. So 0.3 minus 200 into 0. Minus 900 into 0.3 the whole power 4 plus 400. I am getting something of 1.607. So if you find any value which is contradicting with what you got, please inform me. Okay, so I have just one more point to do. 0.45 I will do now. The point why I am doing is I just want to show that if you are using a 5-point quadrature, we will get accurate answer. Hope my calculations are all correct, so that plus minus 900. I am getting something like 2.934875. I need to recheck maybe once. I think it's okay, but let me recheck once again. Two point 934875. Okay, it seems to be fine. So now what you have to do is you have to simply multiply both the columns into 7. I'll write in fraction terms. One 0423 by 250. I'll probably write this. Okay, 1.607 into 12. Let me try to sum everything. Two 2.006. I have to multiply this 0.6. Why this 0.6? Because we saw that in the formula we have the 0.6 into the thing. 1.2036 I am getting. What was the thing? Yes, if you see here, exact is 1.2036. The calculated value is 1.1172 for this was for a 4 point. But when we increase the number of quadrature points to 5, I am getting the exact answer equal to exact 5 point. Okay, so now I have demonstrated the fact that when you have a polynomial of fifth degree, then if you use a 5-point quadrature for Newton codes, you are getting the exact value. So, but if we had gone for the Gauss, what would be the requirement of R? We would have got the same answer for a 3-point quadrature. So here we want to go up to 5 point, then only you are getting the exact value. Okay, so this was the 10th question, sorry 9th question. So I think we will stop here since we have already crossed our thing. So what answer was for 4 point, what was the answer? 1.1172. 5th point 1.2036, right? This was equal to exact. Okay, so I will stop here. So any doubts in what we discussed? So question 9 questions we totally discussed, of which some were subjective, some were objective. Any doubts?
Sir, we'll practice it, sir. We'll practice
Sure,
and
sure.
come back.
Yeah, sure. Yeah, okay, sure. So you can practice the questions. So whatever questions, I will be uploading the this presentation also. So you can see same questions you can also practice, and if you have any doubt, I will explain in the next session. You can raise the doubt. Is it okay?
Okay, sir. Okay.
Yes, okay. So I think we have 2 hours is over. So shall we close the meeting, or is
Sir,
there any?
Sir?
Yes. Yes.
Sir, are you uploading the things in the form of PDF or recording?
Both I am both recording as well as the presentation I am uploading. So you can, if you are able to see in the course, maybe I can show you.
So no issue. I will.
Yeah. Okay. So
Just show
Okay.
me, sir.
yeah.
Show me
I
how to
will.
do it.
Sure. I will show you. If you go here, I have also logged in through my thing. So you can go to this course. So here you can see problem solving session, right?
Yes, sir. Correct. Yeah. I have
If you
followed it.
click, if you click here, it will. Yeah, you can. Yes, it will go here. So you can see that in my name, I'm Vikram Balaji. So
Yes,
I am conducting every Monday, and my colleague Umair Hussain is conducting every Tuesdays 7 to 9.
Yes, sir.
Yeah. So if you see here, I am uploading the this thing presentation thing. So this is the presentation. If you go here, you can get this thing. This one you can download. So YouTube, I think. Yes, YouTube. I'll inform you. This is only the presentation. Okay.
So it is only not YouTube.
Yeah, this presentation, this YouTube, this recording I am uploading in YouTube. The link I will post it. Maybe next session I will post it. Okay, so or if you want now, I can maybe search for the I in the first session when I introduced, I showed the link for everybody. So if you click here, so this is the videos YouTube channel. I'll copy paste this and I'll paste it in the chat section.
Okay.
One thing I can do. So here, if this is a chat box, right? So I'll just paste it here. So this link you can go. So this is my channel. So if you go to the playlist, there are 3 playlists actually. So this is the basics of the finite element analysis.
Okay.
So these are 3 playlists. So till now, week 1, week 2, week 3 I have uploaded here. So week 4, once this recording stop, I will upload this also here. So you can see this, right?
Yes, sir. We will follow.
Yeah. Yes, yes.
Thank
So
you,
this
sir.
link you can note it down. So I have pasted it. You can copy paste somewhere in your desktop. Okay. So this link.
I already taken screenshots, sir.
Ah, very good, very good. Okay.
Thank you,
Okay.
sir.
So if there are no more doubts, we'll close the session now. We can meet next week, same time, 6 to 8.
Thank you, sir.
Okay. Okay. I will stop the recording.